Hi, welcome to this session after the great introduction to Mocha and Dendrise from Sam. My name is Akhil. In this session, we will learn how to develop a parametric workflow to create lattice structures using box grid lattices. Please open the file box grid lattices starter. If you have successfully installed Mocha and Dendrise, you will find them in the ribbon menu by their respective names. So let's move on to developing the workflow now. In the first step, we have to import the design and the non-design spaces of the part. So the design space is a volume which will be filled with lattices, and the non-design space is something that we will not disturb. At the end, the lattices of the design space will be combined with the non-design space to create a final lattice structure. So in this example, we have the internalized data of the suspension arm as we see in the viewer. One can also import externally created CAD models using different translators here, import geometry, parasolid, step, CATIA, and so on. So let's move to the next step. So first we will create the skeleton of the lattice by creating a grid of small boxes with the desired dimensions. So we can use this component called Cel Grid from body, and then here we can define the dimensions in the x direction, y direction, and z direction of the part. So by default, the orientation of the cells are in the global XY plane. So one can also define a custom orientation of the cells by defining a transformation matrix. So please check out the help to understand how to define a transformation matrix and achieve a desired orientation of the cells. So this is where we define the cell topology that we want to populate the grid with. We can also do this in the later stage. Here we can see that the Cel grid is larger than the given geometry. This is to make sure that the whole part is populated with the grid. So in the next step, we can trim the Cel grid using this component, trim Cel grid, and define the body. So here we have also a couple of other inputs to define how the trimming should be carried out. So here we have two different methods. One is the centroidal method and the other one is the corner count. So here you can see the grid is trimmed now. Using the centroidal method, the cells whose centroid are inside this body will be considered, and those cells which are outside would be trimmed off. And using the corner count, we will define also another input here, that is the number of corners. So based on this number of corners that we define, those cells would be considered as inside the design space. For instance, if we define 3 as the corner count, the cells who has their 3 of the corners inside this body would be considered, and all the other cells would be trimmed off. We also have another input on the component, which is fit. If we turn this on, the corners will be expanded or contracted based on the body, and it will fit the given body. So here we can see that the grid is fit to the given trimming body. So with this, we have created the basic grid of the lattice structure. So we can connect to the grid here and move on to the next step. So now we can populate this grid with the desired cell topology. So we can do that using this component populate Cel Grid, and here we can use this component pre-made cells, which has a couple of different type of cell topologies. So if you only visualize the pre-made cells component in the viewer, here you can see how the different cells look like, and the same cell will be populated over the grid. And now we have the final lattice skeleton. So we can extract the curves using the component, extract grid geometry, and we have the curves here. So let's move to the next step to post-process these curves a bit before creating the final lattice structure. So here we have the curves and here we have the non-design space. And we can see that some of the curves are inside the non-design space, which is not desired. So hence we can remove those curves. We can do that by evaluating the curve using this component at a parameter 0.5. So this gives the midpoint of all the curves. And then we can calculate the closest point to the non-design space using this component body closest point. And then this gives out all the points which are closest to this midpoints of the curves on the non-design space. And here we can also get the distance. So let's calculate if the distance is less than 0.7. That means here we are setting a threshold value. And then we say that remove those curves. And with dispatch, now we can get the final curves. And here we can see that now the curves are clean and none of them are in the non-design space. So let's move to the next step now to create the radius of these curves. So we can directly make use of these curves and using the component construct pipe curve, we can define the radius, for instance like this. So this will create a constant radius across all the curves. Or we can also use fields and define the radius here. So for instance, let us have more radius of the beams towards the non-design spaces. That means towards the region where it is interfacing and connecting with the non-design space. And at all other regions, we define the constant value of the radius, which is 0.5. So here we can visualize the field using this component, visualize field and give a particular geometry. And here we can see how the field looks like. So here we can observe that the field value at the non-design spaces is 1. That means the radius of the beams towards this region is 1. And it slowly transitions from 1 to 0.5 when it is coming towards the design space. And this transition distance is something that we can define here. So one can also reduce the transition distance and increase the degree at which it is transitioning. So in this case, it's a linear degree. One can also define a higher order polynomial here. So let us use this field now to create the beams. So for now we can delete this component and use the other component called as beam evaluate field. So you can also find all the Mocha components in here. So we can define the resolution, that means the number of points on the curve at which this field will be evaluated. And we can define the beams, that means the curves that we have extracted and the field. So this component creates the pipe curves with the radii based on the field. So here we can observe that the radius at the non-design space is high. So let us create the volume in the next step. So let's move to the next step. So here we will convert the pipe curves into volumes. So here we have the pipe curves and we can use this component called as pipe curves to volume, which is this one, and this will convert them into a dendrise volume. So as we have learned from the introduction video, we will make use of dendrise to create the volumes and the meshes for all the lattice skeletons that we have created before. So as we can see, this component needs an additional input which is called settings. So here we will define the settings of the voxels. So here we can define the size of the voxel. So please remember that the size of the voxel should be at least 33% of the radius of the pipe curves, so that the cross section of the beams can be accurately represented. So we can use this volume settings and here So now we have the volumes of the lattice curve. Here we can clearly observe that the radius is high towards the non-design region. We can also export these volumes as .vdb file using these components export volume, and the exported volume can also be imported back again like this. So now we have the lattice beams, and in the next step we will combine these lattice beams with the non-design space. So here we have the non-design space, which is a solid body. So to convert them into the volumes, so first we have to create the mesh using this component body to mesh, and then using this component mesh to volume, we can create the volume of the non-design space. So here, as we can observe, that these settings are same as the one that are used for the lattice beams. So please try to use same settings for all the volume creation in the workflow in order for the Boolean operations to be successfully executed. So now we have the lattice volume and the non-design space volume. So we can use this component volume union to union them together. This one. So here we can observe that now we have achieved the final lattice structure. So we can convert this volume into mesh using this component volume to mesh, and at the end we achieve the final lattice structure. So we can also export the lattice structure using the component export stl and then define your file name. So you can define the file name like this. So this is how we can parametrically develop a workflow to create lattice structures for the given part. So now if we go to the step to extract the lattice curves, here we have different types of cells. So one can simply switch between different cell topologies and achieve a different lattice structure. And one can also create custom cells using this component, create cubic unit cell and create a custom cell of their own. So please check out this example file to learn how to create a custom cell. And if we move to the first step where we have created the basic lattice skeleton, we have used this component Cel Grid from body, and here we have defined the size of the grid, that means the size of the cell in x, y and z direction. So here one can also do it slightly differently using the other component, which is create Cel Grid, and here we can also define the number of cells that we want in each direction. So feel free to switch between different components based on the requirement. So here we have created a lattice structure for the closed volume. Sometimes there could also be other requirements to create a lattice skeleton between two irregular surfaces. So how can we do that? Here we have this component Cel Grid from surfaces, and if we go to the example file, here it's clearly explained how can we create a grid that can follow the shape of the irregular surfaces, and it should be between two surfaces. So from here we can get the grid and follow the same procedure as explained before. So we can extract the Cel Grid to get the curves and then follow on to the Dendrise components to create the lattice structure. So this is the end of this session, Grid Lattices. In the next session, we will learn how to create conformal lattices.